So finally, for this week's subspace projections, and we'll have a look at genetic algorithms as promised and on feature clustering. So we start with genetic algorithms. So the general idea is somehow to model this randomized procedure of mutation and selection in the evolution of genetic material of life forms. So to somehow guide this kind of randomized search by modeling this the evolution more or less. Yeah. So in general, genetic algorithms typically encode individual states in the search space as bit strings. What are the states in the search space? Well, that are the feature subsets. Yeah, that are the projections we want to have. So if we again want to have a k-dimensional subspace of our original feature space, and the original feature space has n dimensions, these n over k candidate states, or candidate projections are the individual states of the search space. So that is the set of the search space actually. Yeah? And we encode each member, which is each subspace, each k-dimensional subspace, as a bit string modeling an individual state in the genetic algorithm. Yeah? So the population, our current set of solutions, is a subset of all possible k-dimensional subspaces. And of course we need a kind of fitness function, which is of course again a quality measure for a subspace. Yeah, and the algorithmic schema to find the best solution in the search space of all possible k-dimensional subspaces, as I said before, is inspired by nature. So we try to mix and change the population. So we keep a population, a small set of candidates. That is our current solution. That are our current solutions, and we get from one population to the next population by just mixing and changing the population from one step in the iteration to the next. And we may stop through different criteria. For example, if the best solution of the current population is less fit, according to the fitness function, has less quality than the best solution of the previous population, or after a given number of populations and stuff like that. Yeah? So there are different stop criteria around. Yeah? So genetic algorithms have different variations, and we here just report, so to say, the most generic properties. Yeah, and each iteration manages a specific population from which the next population is obtained by mixing and changing. And let's have a look at how this is actually obtained. Yeah, so we have specific operators on the current populations, which are k-dimensional subspace candidates. Yeah. To generate new candidates for the next population, so new k-dimensional subspaces. And there are the two basic operations. Sometimes we have other two, but in that case, or the basic genetic algorithmic schema is that we have mutation. So that means a specific dimension, a specific feature in the subspace of the current population is replaced by some other dimensions with a likelihood of some percentage, and this replacement leads to a new candidate in the next population. And the second operator to create a new candidate in the next population from the current population or the previous population is crossover, where we combine two subspaces, R1 and R2, meaning that we unite the feature sets of R1 and R2, for example, by an AND or an OR operation if we have bit strings, and delete random dimensions until the dimensionality is k again. Yeah? So that would not be just one AND and OR, so we can just concatenate the feature sets and then delete random dimensions until we have again k dimensions. Yeah? And then we have also a selection for the next population. So all subspaces having at least a quality of something %, so X% for the mutation and Y percentage are very often input parameters here. So Y% of the best fit the best, the qualities, the subspaces having the best fitness, the best quality in the current generation are copied to the next generation. Yeah, so we keep the best Y percentage of the current population for the next population, because we think that they are already good, but generate 1 minus Y% new candidates using mutation and crossover. Yeah? And then also sometimes we can use so-called free tickets, or in some variations we can have free tickets, like additionally each subspace is copied into the next generation with a probability of U%, regardless of being among the top Y%. Yeah? So all those U, Y, and X, as I've said before, are additional input parameters, additional to K, the number of features that I want to have, the target dimensionality, of course. Yeah? And as I said before, there are many other variants on this basic algorithmic schema. So different operations, more efficient conversions by so-called simulating annealing. So in that case, the likelihood of free tickets, free tickets here decrease with the iterations. That is called simulating annealing, and so on and so on and so on. So there are different variations of these genetic algorithms here. And they, as you see, they have a lot of randomness, but still they try to somehow guide this randomness to get better results. Yeah? But on the other hand, they are obviously heuristic. So genetic algorithms don't guarantee the optimal result. Yeah? That have to be clear. Yeah, advantages: it can escape from local optima during the search, which is not the case in branch and bound. This is a different thing, but in best first search, yeah, and often good approximations of the optimal solutions are found because of these escape from local optima. Yeah? Because of this mutation crossover, free tickets and stuff like that. Especially mutation crossover, of course, help in getting out of local maxima or local optima. Yeah? Limitations: well, runtime is often not bounded, at least in the original schema. That is easy to solve with additional parameters like the number of populations I look at, the number of iterations I use. However, still the configuration depends on many parameters. I mean, we just get to know about 3 additional parameters. If we want to bound the runtime or the number of iterations, we introduce another one and another one and another one, and all these parameters, of course, have to be tuned to achieve good quality results in efficient time. So also hyperparameter tuning here in genetic algorithms are a topic on its own, so to say. Yeah? So keep that in mind, that genetic algorithms are nice, but they introduce a lot of different heuristics in terms of parameters that, of course, could be optimized. And hyperparameter optimization is always something which costs time and resources, probably.